Section 2.4, Chemical Formulas. Chemical formulas are a way to represent what molecules are made up of and what they look like. So primarily we're talking about the symbolic domain here. They can simply tell how many of each atom is in the molecule, but they can also give information about how the molecule is arranged and its three-dimensional shape. So here are two different examples of how chemical formulas may be written. So here we've got CH4, this is methane, plus O2, oxygen gas. So these are the reactants, and they form carbon dioxide, CO2, and water, H2O. So here the chemical formula for methane tells you that you've got one carbon atom and four hydrogen atoms in this compound. Here we've got oxygen gas, so we've got two oxygen gas molecules. So we've got two oxygen gas molecules, each composed of two oxygen atoms, carbon dioxide, and water here. So there are a few different formulas. There's the molecular formula. So the molecular formula is far and away the most common formula that we'll be using in this course. Now there's also the structural formula. We're not going to see this as commonly. We'll see it a bit in chapter 4 when we get to Lewis structures. You'll see this a bit more often if you go on to organic chemistry. Now there's also what's called the ball and stick model and the space filling model. So we won't see these very much except when we get into molecular structure, because these two models, they are not extremely useful if we're trying to do chemistry quickly, but they can be helpful for describing how these molecules or how these compounds are arranged in three-dimensional space. So here we see the four different representations of methane, and here we see three different representations of sulfur. So the structural formula, the ball and stick model, the space filling model for sulfur. The molecular formula for sulfur here would be S with the subscript of 8. Now let's quickly talk about the difference between subscripts and coefficients, because there is a very key difference between them. Now coefficients, those are the numbers in front, and they represent separate entities. Now if you don't see a coefficient written, it's assumed that we have a coefficient of 1. So here there's an assumed coefficient of 1. So that coefficient of 1 means we have one H atom. Or if I write 2H, this means I have two H atoms. Now subscripts, those numbers in the bottom right, they represent things bonded together. So if I write H2, this means I have one H2 molecule, or this means I have two H atoms bonded together. So 2H represents two individual hydrogen atoms, whereas H2 represents one H2 molecule. It's two hydrogen atoms that are bonded together to form one molecule. So then finally, 2H2 would represent two H atoms, or two H2 molecules, each composed of two H atoms bonded together. All right, next, let's look at the empirical formula. So we'll get more into the empirical formula in chapter 6, but for now, I just want to talk about what empirical formulas are. And empirical formulas, they indicate the types of atoms present, and importantly, they represent the simplest whole number ratio of the number of atoms or ions in the compound. So for example, benzene. You'll see benzene a lot if you go onto organic chemistry. You may have heard of benzene before. It's used in a lot of industrial products and processes. Now benzene is a bit problematic as it is a carcinogenic. So if you're exposed to high doses of benzene, you have much higher cancer rates. Now benzene has the chemical formula C6H6. So this is what benzene looks like structurally. Here is the structural model, so ball and stick model, structural model, and the space filling model of benzene. So a chemical formula of C6H6. Now you'll notice we've got 6 carbon atoms, 6 hydrogen atoms. So while the chemical or molecular formula of benzene is C6H6, its empirical formula is CH, because the empirical formula represents the simplest whole number ratio of the number of atoms in the compound. So since both have 6 atoms, we can simplify that, giving an empirical formula of CH. Let's look at something like acetic acid. So acetic acid is a weak acid. It is the primary component of vinegar. So here is the structural formula of acetic acid. It has a molecular formula of C2H4O2, 2 carbon atoms, 4 hydrogen atoms and 2 oxygen atoms. So this is its molecular or its chemical formula, C2H4O2. Now you'll notice here that all the subscripts can be divided by 2, which means the empirical formula of acetic acid is CH2O. Alright, let's try a knowledge check question. What is the empirical formula for a compound with a molecular formula of C4H8O2? Alright, the correct answer here is C. It is C2H4O. You should notice that all 3 of these are divisible by 2. So when you divide them all by 2, you get C2H4O. Alright, let's talk about structural isomers. So isomers are compounds that have the same chemical or molecular formula, but something about them is different. So specifically, structural isomers, they have the same types of atoms, so they have the same molecular formula, but they are connected together in different ways. So if we look at acetic acid versus methyl formate. So acetic acid and methyl formate, they have the same types of atoms. They have the same molecular formula, C2H4O2. But these atoms are connected in different ways. In acetic acid, we've got carbon. This carbon atom is double bonded to oxygen, single bonded to this oxygen atom, and then single bonded to carbon. Whereas here, that carbon atom, the oxygen is on this side, so it's double bonded to oxygen, single bonded to hydrogen, single bonded to oxygen, and then the CH3 group is over on the left here. So the atoms are connected together in different ways. These are called structural isomers. Another type of isomers are what are called spatial isomers. So this is not something that's going to be on the exam. This is something you'll encounter if you go into organic chemistry. So spatial isomers are really interesting. Spatial isomers, they have the same molecular formula, but they also have the same structural formula. They are connected together in the same way. How are they different? Well, they are arranged differently in 3-dimensional space. They are spatially different. So for example, if we look at the amino acid carvone, carvone has 2 different forms. There's R and there's S. So these 2 isomers, they have the exact same molecular formula. They also have the same structural formula, but they are arranged differently in 3-dimensional space. They are mirror images of one another. Specifically, they are what are called non-superimposable mirror images. The word for these are called enantiomers. You will learn about them if you go to organic chemistry. Kind of like your hands. How your hands have the same, quote, molecular formula. Your hands also are the same structurally, but your hands, they are non-superimposable mirror images of one another. They are arranged differently in 3-dimensional space. So this is what spatial isomers are. Alright, now let's move into talking about a mole. So a mole is an extremely important concept in chemistry, and it is the official SI unit for the amount of a substance. So where does this word come from? Well, it comes from Latin. The word mole in Latin means massive heap. So in chemistry, our heap, it is made of particles, either atoms or molecules. So a mole is really just a way of counting things. So for example, if I said I have a pair of shoes, I could say that I have 1 pair of shoes, or I could say that I have 2 shoes. They mean the same as one another. So the word pair is just a way of counting. Or I could say that I have a dozen eggs, right? I could say that I have 1 dozen eggs, or I could say that I have 12 eggs. The word dozen here is just a substitute. It's just a way of counting a number in a more convenient way. I could also say that I have a ream of paper. So the word ream, with regards to paper, just means 500. I could say that I have 1 ream of paper, or I could say that I have 500 sheets of paper. It's just much more convenient to say 1 ream. So a ream is just functioning as a counting number. So a mole is the exact same thing. It is the exact same logic as the 3 previous examples. It is just a much bigger number because molecules, they are so small. So 1 mole represents 6.022 times 10 to the 23rd. This is what's called Avogadro's number. So you are going to want to memorize this number. 1 mole equals 6.022 times 10 to the 23rd. So just how big of a number are we talking here? What does 10 to the 23rd even mean, right? It's kind of hard to conceptualize that. So 1 mole of jelly beans could fill the Empire State Building 2 trillion times. So a mole is a massive, massive number here. So this just really illustrates how small atoms and molecules really are. What can we measure with the mole? Well, as I mentioned, the mole, it is great. It is great for measuring the amounts of chemicals because atoms and molecules, they are just so small. So here, this image represents a mole. This is a mole of aluminum, or a mole of copper, a mole of water, a mole of salts, a mole of sugar, a mole of helium inside the balloon. All of these elements, these compounds here, they are all present in 1 mole. But they're just a mole is just really the number of atoms or the number of molecules present. So Avogadro's number, it's really useful for us because it can be used as a conversion factor. We can say that 1 mole of atoms equals 6.022 times 10 to the 23rd atoms. So because these two things are mathematically equal to one another, we can use them as a conversion factor, and so we can arrange them as a ratio in either direction. We can put 1 mole on top and the number of atoms on the bottom, or we can put the number of atoms on top and mole on the bottom, depending upon what conversion we are trying to do. Alright, so let's look at an example. Suppose that I ask you to determine the number of calcium atoms in 30 moles of calcium. So we've got 30 moles of calcium, that is our starting value, and I want you to determine the number of calcium atoms. Well, what you should do here is you should realize, okay, I've got moles, I'm being asked to find atoms, how do I relate moles and atoms? Avogadro's number. So what you should do then is use Avogadro's number as a ratio. Put the value on the bottom, put the value you're trying to go away from on the bottom, put the value you're trying to go towards on top. So I'm trying to eliminate moles, so I'm going to put 1 mole calcium on the bottom, and I'm trying to determine the number of atoms, so I'm going to put 6.022 times 10 to the 23rd atoms in my numerator. So 30 times 6.022 times 10 to the 23rd gives 1.807 times 10 to the 25th atoms. And you can see moles cancels, leaving the unit atoms. Suppose I asked you to do the reverse. Determine the number of moles of calcium in a sample containing 1.00 times 10 to the 20th calcium atoms. So again, if you receive this word problem, you should think to yourself, okay, what value am I given? I'm given the number of calcium atoms. What am I being asked to solve for? The number of moles. So I should use Avogadro's number. So I've got 1.00 times 10 to the 20th atoms. So I should put 6.022 times 10 to the 23rd on the bottom, so that way atoms cancel, and I put 1 mole on top. So atoms cancel, which leaves moles. So 1.022 times 10 to the 20th, essentially divided by 6.022 times 10 to the 23rd, gives 1.66 times 10 to the negative 4th moles calcium. Alright, let's talk about our final major concept of this chapter, and it is molar mass. The molar mass of a substance is the mass in grams of 1 mole of the substance. So the same number from the periodic table that works for mass of an atom in AMU also works for the mass of a mole of atoms in grams. So for example, if you got a periodic table handy, look at the atomic mass there listed for hydrogen. You should see 1.008, or you might see 1.01 depending upon the precision of the table you're looking at. So the molar mass of hydrogen is 1.008 grams. This means 1 mole of hydrogen atoms has a mass of 1.008 grams. And molar mass, it has units of grams per mole. This is to facilitate cancellation of units in calculations. So here is an image that shows 1 mole of various elements. We've got zinc, carbon, magnesium, copper, sulfur, silicon, lead, and tin. So in every image here, we have the same number of atoms. This is 6.022 times 10 to the 23rd atoms of zinc, 6.022 times 10 to the 23rd atoms of carbon. You get the idea. Same number of atoms in each image. We've just got different masses because each atom it has a different size to it. 12.0 grams of carbon, 65.4 grams of zinc, 28.1 grams of silicon. So these would be the molar masses of these elements. Avogadro's number can also be used for molecules. So this image here represents 1 mole of molecule. So I've got 1 mole of sulfur molecules, 1 mole of octanol molecules, 1 mole of mercury iodide, 1 mole of methanol. So Avogadro's number can be used for atoms. It can also be used for molecules. So let's look at a conversion example, grams to moles. This problem states, according to nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in moles? All right, so in a problem like this, you should see, well, I've been given a mass value. I've got 4.7 grams of potassium. They are asking me to find the estimated average requirement in moles. So I need to convert from grams to moles. So if I'm converting between grams and moles, or, if I'm converting from moles to grams, I can relate those two concepts with molar mass. So find potassium in the periodic table and determine what its molar mass is. So potassium has an elemental symbol of K. Its molar mass is 39.10 grams. So potassium, 1 mole of potassium has a mass of 39.10 grams. So I can use that molar mass as a conversion factor, just like I can with Avogadro's number. So I'm trying to go away from grams, I'm trying to eliminate grams, and I want my final answer to have units of moles. So use that molar mass as a conversion factor and write grams on the bottom. So I would write 39.10 grams potassium on the bottom, 1 mole potassium here in the numerator. So 4.7 grams potassium, so I've got grams on top, grams on the bottom, grams cancel. So 4.7 divided by 39.10, only remaining unit is moles, and I get 0.12 moles potassium. Let's look at a moles to grams example. Suppose I give you the problem that states a liter of air contains 9.2 times 10 to the negative 4th moles argon. What is the mass of argon in a liter of air? So here you are trying to go from moles to grams. So once again, if you're going from moles to grams or grams to moles, you relate these two values with the molar mass. So find argon in the periodic table is the elemental symbol Ar. Its molar mass is 39.95 grams. Now here, I am starting with moles, and I want my final answer to have units of grams. So when I use that molar mass as my conversion factor, I should write moles on the bottom, since I want moles to cancel, and I'll write grams on top. So 9.2 times 10 to the negative 4th times 39.95 gives 0.037 grams argon. Alright, now let's look at a grams to moles to atoms example. This problem states, copper is commonly used to fabricate electrical wire. How many copper atoms are in 5 grams of copper wire? So we are starting with grams, we're starting with a mass, and the problem is asking you to find atoms. So you cannot go directly from grams to atoms. You need an in-between step. You first need to go from grams to moles. And so to go from grams to moles, you need to use the molar mass. So use the molar mass to convert from mass carbon, from grams carbon to, copper to moles copper. Then you can go from moles copper to copper atoms using Avogadro's number. So again, you cannot convert directly from grams to atoms. You first need to convert to moles, then from moles to atoms. So my first step is I'm going to convert from grams to moles using the molar mass of copper, which is 63.55 grams. So I've got 5 grams copper. I'm going to use that molar mass as a conversion factor and put grams copper on the bottom, 63.55 grams copper on the bottom, so this way grams copper cancel, and 1 mole copper up top. Now I'm going to chain this together in one long calculation. If I stopped here, my units would be moles copper, but I want atoms. So I'm going to use Avogadro's number as my conversion factor. So I'm going to write 1 mole copper on the bottom. Now moles copper cancels. And I'll write 6.022 times 10 to the 23rd atoms copper on top. So grams cancel, moles cancel, only unit left is atoms. So I take 5 times 6.022 times 10 to the 23rd divided by 63.55, and this gives 4.74 times 10 to the 22nd atoms copper. All right, let's try a knowledge check question. How many atoms of magnesium are in 0.546 moles of magnesium? So you need to convert from moles to atoms. All right, the correct answer here is D, 3.29 times 10 to the 23rd. So you should recognize if I'm trying to convert from moles to atoms, I need to use Avogadro's number. So when I write this calculation out, I've got 0.546 moles magnesium, and I'm going to use Avogadro's number as a conversion factor. I would write 1 mole magnesium on the bottom and 6.022 times 10 to the 23rd atoms magnesium. Again, sorry about my handwriting, working on a touch screen. 6.022 times 10 to the 23rd atoms magnesium on top. This way moles magnesium cancel, and my only unit left would be atoms magnesium. So 0.546 multiplied by 6.022 times 10 to the 23rd gives D, 3.29 times 10 to the 23rd atoms. All right, finally, let's talk about molar mass of a compound. So before, we were just talking about molar masses of elements. The molar mass of a compound is the sum of molar masses of the elements it contains. For example, if I asked you to find the molar mass of water, you would sum the molar masses of its component elements. So we've got 2 atoms of hydrogen, so 2 times 1.008, plus 1 atom of oxygen, 16.00. So 2 times 1.008 plus 16.00, this rounds to 18.02 grams. So water has a molar mass of 18.02 grams. If I asked you to do this for salt, sodium chloride, NaCl, so I wanted to find the molar mass of sodium chloride, it would be the mass of 1 atom of sodium, 22.99, plus the mass of 1 atom of chlorine, 35.45. Excuse me, 1 mole of sodium and 1 mole of chlorine. This gives me a molar mass of 58.44 grams. So sodium chloride, NaCl, has a molar mass of 58.44 grams. So again, to find the molar mass of a compound, you simply just need to sum the molar masses of the elements it contains. All right, quick knowledge check question. What is the molar mass of ethanol, C2H6O, in grams per mole? All right, correct answer here is C, 46.069 grams per mole. So you should have 2 atoms of carbon, so 2 times 12.011, plus 6 atoms of hydrogen, 6 times 1.008, plus 1 atom of oxygen, which I remember as 15.999, but you could also use 16.0. And when you sum these together, you should get 46.069, or you may have gotten 46.07 if you rounded to 2 decimal places. All right, let's briefly talk about compounds with parentheses. Now, if you see a compound with parentheses and you've got a subscript on the outside of the parentheses, that subscript applies to all of the atoms inside the parentheses. So you need to multiply that subscript on the outside by the subscript inside. So for example, to find the molar mass of this compound is called magnesium hydroxide. It's Mg parentheses OH2. We would use, well, we've got 1 atom of magnesium, so that unseen subscript of 1, plus 2 atoms of oxygen, right? So inside the parenthesis, we've got a 1, so 2 times 1 gives 2 atoms of oxygen, plus 2 atoms of hydrogen. So it should be 1 atom of magnesium, 2 atoms of oxygen, 2 atoms of hydrogen. So it's kind of like distributing in algebra. You distribute the 2. 2 times 1, 2 times 1 gives 2 atoms of oxygen, 2 atoms of hydrogen. All right, let's look at an example of grams to moles of a compound. This problem states our bodies synthesize protein from amino acids. One of these amino acids is glycine, which has the molecular formula C2H5O2N. How many moles of glycine molecules are contained in 28.35 grams of glycine? So here you're being asked to find moles, and you are given a mass. So we've got 28.35 grams of glycine, and we want to find moles. So how do we go from grams to moles? We need the molar mass. So the first thing we should do is find the molar mass of glycine. So we've got 2 carbon atoms, 5 hydrogen atoms, 2 oxygen atoms, and 1 nitrogen atom. So you sum these together and you get a molar mass of 75.07. So glycine has a molar mass of 75.07 grams per mole. So this is my molar mass. This is the conversion factor I'm going to use. Now remember, we started with mass and we want to find moles. So I've got 28.35 grams glycine, and I'm going to use that molar mass like a conversion factor. Since I'm trying to get rid of grams, I should write 75.07 grams in the denominator and 1 mole in the numerator. This way, grams cancels, leaving the unit mole. So 28.35 divided by 75.07 gives 0.378 moles glycine. All right, let's look at a reverse example, moles to grams of a compound. Vitamin C is a covalent compound with the molecular formula C6H8O6. The recommended daily dietary allowance of vitamin C for children aged 4 to 8 years is 1.42 times 10 to the negative 4th moles. What is the mass of this allowance in grams? So here we've got moles, and we want to find grams, so we're going in the reverse direction. But again, how do we relate moles and grams? We use the molar mass. So we need to find the molar mass of vitamin C. So I'm not showing the work here, but if you go through and you find the molar mass of this compound, so 6 atoms of carbon, 8 atoms of hydrogen, 6 atoms of oxygen, you should get a molar mass of around 176.124 grams. So this is my molar mass. I'm going to use this as a conversion factor. I'm starting with moles. I'm trying to get 2 grams, so I should write moles on the bottom. This way, units of moles cancel, and I'll write grams on top, so that's my unit remaining. So 1.42 times 10 to the negative 4th multiplied by 176.124 gives 0.0250 grams. So the dietary allowance of vitamin C is about 0.0250 grams. All right, finally, let's look at a grams to moles to molecules to atoms example. So we're making it a little more complicated. This problem states a packet of artificial sweetener contains 40 grams of saccharin, which has the molecular formula C7H5NO3S. Given that saccharin has a molar mass of 183.18 grams per mole, how many saccharin molecules are in a 40 milligram sample of saccharin? How many carbon atoms are in the same sample? All right, so first let's do the first part of the problem here. We are being asked to find saccharin molecules, and we are starting with mass. So you should think to yourself, okay, I've got mass. First, I need to go to moles using the molar mass of the compound. Then, once I have moles, I can find molecules using Avogadro's number. Remember, you cannot go directly from mass to atoms or molecules. You have to go to moles first, then you can go to molecules. So I've got 0.0400 grams saccharin, and I'm going to divide by the molar mass to find the moles saccharin. Once I've got moles saccharin, I can find molecules using Avogadro's number. So I've got grams on the bottom, this way grams cancel, and I've got moles up top. Now when I use Avogadro's number, I'm going to put moles on the bottom, so moles on the bottom cancels with the moles on top. And I'm going to put molecules on the top here, so the final unit remaining is molecules. So 0.04 times 6.022 times 10 to the 23rd divided by 183.18 gives 1.31 times 10 to the 20th. So in 40 milligrams of saccharin, there are 1.31 times 10 to the 20th molecules of saccharin. Now the second part of the question asked how many carbon atoms are in the same sample. So I want you to think about this. If I have 1 molecule of saccharin, how many carbon atoms do I have? 1, 2, 3, 4, 5, 6, 7. So I have 7 carbon atoms for every 1 molecule of saccharin. So I want to use that ratio as my conversion factor. For every 1 molecule of saccharin, there are 7 carbon atoms. So I should take the number of molecules of saccharin and multiply it by 7 to determine the number of carbon atoms. And this gives 9.20 times 10 to the 20th carbon atoms. Alright, that is the conclusion of Chapter 2. If you have any questions, please do not hesitate to reach out to me via email and check out the textbook links that I've been posting below if you want to go ahead and read the textbook where these most of these images and where this information comes from. So that is the end of Chapter 2. I'll see you in the next videos when we begin Chapter 3.